Good afternoon, and welcome again to a lesson that you should probably cover it in two parts. I don't know exactly how long it will take, but again, this is one of those lessons that require more examples to go through, and the method itself, it's a little bit longer depending on the example at hand. And also because the steps involved when you set up the problems need to be clearly understood, and you have to be patient when you go about the method. So after you understand it, of course. Take a moment to write down the goal. So the idea in this lesson is to be able to integrate functions containing one of these radicals. By a, we mean a constant, a positive constant. So any function that may contain either square root of a squared plus x squared, so basically a positive constant plus x squared, or square root of x squared minus a squared, or the other way around, a squared minus x squared. But importantly, and I'll get back to this point here, the idea is to integrate these functions containing these radicals in the situation that these integrals cannot be solved by other simpler means. At this point, you will learn various methods of integration, and there is a tendency sometimes to use the more complicated method when an easier method will work. So always take a moment, step back, and you look at the problem and see if you really need to come up with something fancier, like in this case, trigonometric substitutions, when maybe a quick substitutions, quick direct substitution, or maybe by parts might work faster. So you reach a point in the course where you have more tools at your disposal, and the same problem can be approached by different tools, and obviously you should choose the one that gives you the least of the headaches, so to speak. So that means you don't work harder than necessary. And before we talk about the trigonometric substitution itself, let me point out that the U substitution that you know about, it's kind of the opposite way of doing the substitution compared to what we're going to do in this lesson. So what we called in calculus U substitution, so let's recall briefly. What we call a U substitution was a method of integrating a function that looks like this. So the composition of two functions times g prime of x, the inner function, and in this case, the idea is to replace a function, the inner function g of x, with a new variable. And then you end up with an integral in u, presumably an integral easier to solve, f of u du. So in the substitution that you learned so far, you replace a portion of the original function with a variable, with the new variable, which you can call it anything you want, but we typically call it u, and therefore that's why we call it U substitution. Today we're going to do kind of the opposite, which may sound strange because it may look like you complicate matters, but you will see immediately that we do that for a good reason. So today we start with a function to integrate. Let's call it f of x dx. And then we replace x with a new function in a new variable, because that new variable will denote actually the angle in a triangle, basically the argument of a trigonometric function. Typically that new variable is denoted by theta, but again you could denote it however you like. So the idea in this case, in this type of new substitution, is we replace x with a function, let's call it g of theta. And again, in order to come up with an integral in theta, you also have to compute the differential of x, just like before. And remember from calculus 1, the differential is g prime of theta d theta. So compare it with the previous case when the existing g prime of x dx became du, because gx was replaced by a new variable u. This is kind of the other way around. So the original variable x is going to be replaced by a new function. Dx becomes g prime of theta d theta, same formula, that's the differentiation formula. or the formula for a differential of a function. And so the integral to start with, when you move on to the unit variable, becomes the integral of f of g of theta times g prime of theta d theta. So again, it looks strange because it seems that, you know, this right-hand side becomes more complicated, but that's not the case thanks to some trigonometric identities. So let's see how this plays out with the radicals that we mentioned here. So the goal is to simplify these radicals. And we're going to start with, let's start with the first one, yeah, with square root of a squared plus x squared. And also let me remind you the trigonometric identities that are useful here, which we already mentioned them in the previous lesson. So remember, we have sine squared of theta plus cosine squared of theta equals 1. And another one in terms of tangent and secant, 1 plus tangent squared is secant squared theta. And if you have a function to integrate that contains the square root of ax squared plus x squared, well, obviously the problem when you have functions like this is that you need to eliminate the square root. That is the reason why we learned this lesson in the first place, right? I mean, that's what makes it complicated in the beginning, right? So how do we eliminate radical to integrate a function containing this radical? Well, notice what happens if I replace x with a, again, a stands for a positive constant, with a tangent of theta. We're not going to be discussing too much the domains of these variables. We'll talk about that maybe later, but notice that this replacement makes sense. I mean, if x can be any real number, which it can, right, because the quantity under the radical is positive, tangent of theta itself, if theta varies between minus pi over 2 and pi over 2, if you remember how the graph of the tangent looks like, between minus pi over 2 and pi over 2, so the tangent covers all real numbers as well. So this replacement covers the entire domain of integration. So if I replace x with tangent of theta, look what happens inside the square root. So let's do some little algebra here. So I have a tangent of theta quantity squared, a squared plus a squared tangent squared theta. Inside the square root, I can pull out a squared. And now the magic happens because we have an identity that replaces 1 plus tangent squared with secant squared. And that is the reason why we made this substitution in the first place. So we managed to basically have a perfect square inside the square root. And then finally this allows me to cancel the radical with the square. Okay, now that is the goal. That is the whole idea, right? That's how we can simplify the radical. So that's the purpose of doing this. Now, of course, in the integral we have more elements than just a secant theta. This is just what the radical becomes after I make this substitution. So you will see with an example right away how that will work. So you can think of this as a rule on how to handle integrals like this, which cannot be solved otherwise. We'll move on to examples right away. I want to finish basically the substitution that you will employ for the other types of integrals, for the other types of radicals that I have here on the top of the page. What do you do if you have square root of a squared minus x squared? Well, here we're going to exploit actually this formula, sine squared plus cosine squared. And here we're going to make the substitution x with a sine of theta. And if I do that, sine squared, I can pull a squared 1 minus sine squared of theta. Moving on, that's going to be a squared cosine squared theta, and then I can cancel the square root with the power a cosine of theta. So again, I eliminate the radical. So if I do the substitution, the radical becomes a cosine of theta. Previously, if I do the substitution, then the radical becomes a secant theta. And then finally, before we move on to actual examples, if I have square root of x squared minus a squared, then we're going to exploit again the formula with the tangent, but by making a substitution for secant. So pay attention how this works out. If I replace this time x with a secant theta, then the square root becomes a secant theta quantity squared minus a squared. A squared secant squared theta minus a squared. Pull out a squared. And now, if you look at the formula over here in the middle, secant squared theta minus 1 is tangent squared. So again, remember, the goal is essentially to have a perfect square inside the radical so that I can simplify the radical. So the idea is like this, and let's write it as a remark before we move on to examples. With these trigonometric substitutions, we eliminate the radical at the price, I put this in the quotation marks, of a trigonometric integral. Because, you know, it can have some hard work to do after that. Remember, in the previous section we did a trigonometric substitution, so you may have to do essentially what you learned in the previous lesson, depending on what you end up with. But if there is no other way to eliminate the radical, you could do this trigonometric substitution, and you end up with a trigonometric integral, which can be easy to solve, or it may require a trigonometric substitution. So the rest of the lesson is devoted to examples of each kind, and I'm going to comment more on the domain of integration and other things like that. Especially if you have a definite integral with the bounds. But before we move on, make sure you understand these computations, because once you have these three procedures, depending on the radical, you can go a little bit faster in the problem. So once you make the substitution, you know what each radical becomes, right? A secant, a tangent, or a cosine theta, depending on the case. And don't forget that when you move on with the actual integral, you have other things to compute here, including this dx, which sometimes people forget it. Remember, dx is replaced by g prime of theta d theta. And that g prime again could be a secant, a tangent, or a sine of theta. So stay tuned for actual examples. Okay, so before we start the example, let's write down again the three substitutions we will perform. I forgot to mention in the previous page that there are some restrictions on the theta, so that the functions is 1-to-1 when you make these substitutions, and to ensure that when you take the radical, you end up with a positive quantity, because otherwise it's the absolute value of a secant here on your, or a cosine when you take those radicals. So for example, when you make the substitution with tangent or a sine of theta in the first two cases, when you take the radical, you end up with a secant or a cosine. And remember, secant is 1 over cosine. Now, the reason you take theta in this case to be between minus pi over 2 and pi over 2 is to ensure that the cosine is positive, right? So if, you know, minus pi over 2 and pi over 2, if you look at the trigonometric circle, will be the right half of it. Right half of the unit circle. So then in that case, the the cosine is positive, which, remember, you read the cosine on the x-axis. Same thing for the tangent. To be positive, you need to be either in the first quadrant or the third one, basically. Either, in other words, both sine and cosine positive or both sine and cosine negative. So that's why in this case theta should be between 0 and pi over 2 over here, or between pi and 3 pi over 2, which is the third quadrant. So these are the assumptions made. Some problems we won't focus on this, but in some problems you have to be careful with this, especially if you have, like I said, actual bounds of integration in the case of the definite Riemann integral. But anyway, let's start with the first example. So let's say we want to integrate x third over square root of x squared plus 4. So you have to basically go slow with these problems because you need to set up some stuff before you move on with the computation. The first thing to do is to analyze the problem and realize that you need to do this in the first place. I'll show you an example later when you don't have to do that. Here we have a square root that basically complicates the matter. We have x third on the top. There is no obvious U substitution that you can perform because you don't see a composition of function and its derivative. So for example, if you think about replacing u with x squared plus 4, that's not going to work because du is going to be 2x dx, but you have x third, unfortunately, instead of just x dx. So then in this case, you may think about a trigonometric substitution. Once you identify the type of radical you have, so this is have to be careful here, right? You are in the first case with a radical of the form a squared plus x squared. In this case, a squared stands for 4, which means a is 2. Remember, you take a to be positive. So that means the substitution to perform is to replace x with 2 tangent of theta. For reasons that you will see later at the end of the problem, place theta in a right triangle so that you can label the sides of that triangle with x or 2, depending on the case, because it will help you later when you move back from theta to x. So one step here to do is to first of all write down the trigonometric function by itself. And remember that in a right triangle, the tangent of an angle, put the angle here, is the opposite side over the adjacent. So because tangent is x over 2, according to the substitution, that means you can label the opposite side by x and the adjacent side by 2. And then compute via Pythagorean theorem the other side. So the hypotenuse is going to be square root of x squared plus 4, right? So from Pythagorean theorem. The reason this is useful is because your answer will depend on various trigonometric functions of theta, and you can write these trigonometric functions easily from the from this triangle. This is basically something you should do when you have an antiderivative to compute. When you have a definite integral, things will be a little bit easier if you change the bounds of integration. I'll show you with an example when the time comes. Once you do this, so you take the substitution, you write the trigonometric function by itself, you label the triangle in the manner I showed you here, then you compute the differential of x. So dx is the derivative of 2 times tangent, so that's 2 secant squared theta d theta. And now it's time to make the substitution. So then my integral becomes 2 tangent of theta, so x is replaced everywhere by 2 tangent of theta to the power 3. And the denominator is going to be 2 tangent of theta quantity squared plus 4. And then dx is 2 secant squared theta d theta. This is the place when you can be a little bit faster if you remember what the radical becomes. So if you remember that your radical becomes a secant theta, you can replace it right away in your case with 2 secant theta. If you don't remember that, just do the computation and apply the identity. So here if I raise to the power of 3, that's 8 tangent third theta. On the denominator I have 4 tangent squared theta plus 4 times 2 secant squared theta. But you see, it's useful to remember what the radical becomes because you save some steps. Let's combine 8 with 2. That makes it 16 tangent third theta secant squared theta. On the bottom I can pull out 4 tangent squared theta plus 1. 16 tangent third secant squared. And 1 plus tangent squared is 4 secant squared. Later on I'm going to just write right away what the radical becomes because we know already from what I wrote here on the top of the page. Secant is positive because we restrict theta to that interval I mentioned before. So go very patiently until you get the hang of it. You'll go faster naturally later, but in the beginning you shouldn't rush the theta. So we can actually cancel a factor of secant, and then 16 over 2 becomes 8. And you're left with the integral of 8 tangent third theta secant theta. So we're not done yet, and as you can see, problems like this can be rather longer than normal, or than what you've seen before, which is the reason why you should go slower on this. So we eliminated the radical, but we ended up with a trigonometric integral. Now we have to remember what we learned in the previous section and see what we can do about it. Sometimes we can be lucky to have a simple integral to solve immediately, otherwise we may have to use some other substitutions. So if you go back to the previous lesson, this falls in the category of a combination tangent secant with an odd power of tangent. And remember, that can be dealt with if we make the substitution u equals secant theta, which calls for separately writing down du, the derivative of u, which is secant tangent d theta. So under that substitution, we will basically pull out the tangent secant separately. So I'm left with tangent squared. Use again the identity to write tangent squared in terms of secant squared, or secant squared minus 1. If you need to take a pause and look back on the previous section, you should do that. And then tangent secant d theta becomes, later will become du, right? So tangent theta secant theta d theta. All right, so let's perform the substitution. Secant is replaced by u, and then du. Expand and integrate. 8 third u third minus 8u. So we have to go back now to the original variable. So notice this problem required in the end 2 substitutions. The first one was the trigonometric substitution, which is the topic of the lesson today. The resulting integral required another typical U substitution, which we learned in the previous lesson. So we go back to x in 2 stages. We're done with the integration step. We go back from u to theta. U was secant theta. So 8 third secant theta to the power of 3 minus 8 secant theta. And here is the place where that triangle in the beginning comes handy. Secant theta is replaced by x. Now secant is, remember, 1 over cosine. Cosine of theta is the, if you look at the triangle, is the adjacent side over the hypotenuse. So the secant is the opposite of that, I mean the reciprocal. So secant theta from that triangle will be the hypotenuse over the adjacent side so you get that from the triangle. And as far as I'm concerned, you can leave the answer like that, but be prepared that in many books you'll see this answer sometimes simplified. One way to simplify it, let's do a couple of extra steps just to see how it can look a little bit different. So at the bottom 2/3 is 8, so 8/3 is multiplied by 1 over 8. And this radical to the power 3, you can take radical to the power 2, which is just x squared plus 4, times the remaining radical. And 8 over 3 is 4. Simplify this. Then you can pull the radical. This is just algebra, by the way, which is optional. I should point out. This is all optional, but just to see how it looks. And then 1/3 x squared plus 4, if I expand that, I don't know if I should expand it, but let's see, x squared over 3 plus 4 over 3 minus 4. And yeah, I mean, I can write the common denominator 3, so you end up with, let's see, x squared plus 4 minus 12. That makes it x squared minus 8. So you can have x squared minus 8 square root of x squared plus 4 over 3. That's pretty much the most you can do in terms of algebra. All right, so before we move on to the next page with other examples, it's very important not to rush. I'm very in the this is a little bit against the trend, so to speak, but if the problem requires multiple steps to think about, you just have to allocate more time, because if you rush, then you lose the logic of the whole thing. And essentially, if you find yourself guessing, that is the kiss of death in math. So let me say that again. If you find yourself guessing through the problem, it's time to stop, take a break, go back to the method, and go through the filter of your thinking. I mean, like which step you should do, and then move on after you do that step, and so on and so forth. Don't try to guess, because that's not gonna achieve anything. All right, so let's hold on for the next page with other examples. All right, so let's do another example, this time one involving a radical that involves the substitution with sine of theta. So here we're gonna have a function involving a squared minus x squared under the radical, which calls for the substitution x equals a sine of theta, which leads to the radical becoming a cosine of theta. All right, so suppose I have to integrate, let's do something similar to the previous case, right? So let's say you have x third divided by square root of 36 minus x squared. Notice I picked these numbers so that they have nice radicals, like 36, but it can be any positive number. So if you had, for instance, 5 minus x squared, that's not the problem, but in that case, a would be square root of 5. So same idea. Okay, so that means in this case, the substitution is x equals 6 sine of theta. Let's prepare that little triangle, so isolate sine. And remember that in a right triangle, sine is the opposite side over hypotenuse. Opposite sine is x, so you write sine as a ratio, right? Opposite over hypotenuse. You can call the hypotenuse 6. And from Pythagorean theorem, by the way, if that's not clear what I'm doing here, remember, you know, if you have a right triangle, that's Pythagorean theorem, right? So that means the other side here, in this case b, would be square root of c squared minus a squared, right? So that means in this case is square root of 36 minus x squared. So remember, we do this because if I need to read later some other trigonometric functions of theta, I can pull them quickly from the triangle. All right, don't forget that we need the differential. So dx is equal to 6 cosine of theta d theta. And now carefully replace everything with theta. So x becomes 6 sine of theta, quantity 3, over the, let's do this faster. We know that the radical becomes a cosine theta. That means it becomes 6 cosine of theta. And dx is another 6 cosine of theta d theta. Okay, so here we have some nice simplification. So 6 cosine of theta cancels. 6/3 is actually 2/16. We can pull that out maybe later. Sine third theta d theta. Unfortunately, this is again not immediate, right? Because it's to the power 3, right? I mean, it's we need to do another substitution, basically a trigonometric substitution. Not a trigonometric substitution. A trigonometric substitution. A U substitution, I meant, to handle the trigonometric integral that we have here, sine third theta d theta. We have sine to an odd power. If there was another cosine here hanging around, that would have been the same case, right? So remember, if you have sine with an odd power, the idea is to make the substitution u with cosine of theta, and then du becomes minus sine of theta d theta. So again, go back to the previous section if necessary. The idea is to save separately a factor of sine to account for du, and then the remaining sine squared is replaced with the equivalent in terms of cosine. So 1 minus cosine squared in this case. So this integral, let's pull this 2/16 out. So that's going to be 1 minus cosine squared theta sine of theta d theta. Move the minus over here, so that means in terms of u, this is 1 minus u squared. Sine theta d theta is minus du. So it's minus u plus u squared du, and then integrate. Minus 1/2 u squared plus 1/3 u third. Sorry, I made a u out of the blue here. I'm sorry about that. That's not so it's minus 1 plus u squared. This is 1. So it's 2/16, the integral of minus 1 plus u squared du. And then the integral is minus u plus 1/3 u third. Okay. Now go back to theta. So u is cosine of theta, so that's minus cosine of theta plus 1/3 cosine third theta. And then finally we get cosine from the triangle in terms of x. So cosine is adjacent side over the hypotenuse. Once again, adjacent side over the hypotenuse to the power 3, and I'm going to leave it like that. Again, this can be simplified further, but let's not waste time with that at this moment. Sometimes you can be lucky and you can end up with the integral in terms of a simple trigonometric function, which I'm going to do next as my next example. But as I do this example, I want you to look carefully and see if you notice something. So I'm going to do this time around a Riemann integral, a definite integral. All right, so let's say I have the integral from 0 to 3 x over square root of 36 minus x squared. So it's very similar to the one before, but we have x on the top. I'm not going to write the triangle again. The same triangle will work here because this essentially requires the same U substitution. So x equals 6 sine of theta. But if you have a definite integral, right, so you do the same steps. Remember the importance of changing the bounds of integration. And here you may use the calculator if necessary, if you don't remember the bounds essentially, although sometimes those bounds are obvious if you remember some trigonometric function values. So once again, when you do the triangle, you need to isolate sine of theta, x over 6. Again, this leads to the same triangle. I'm not going to sketch it again with the opposite over the hypotenuse. So you label the opposite by x and the hypotenuse by 6. But you also have to change the bounds of integration. And here you have to be careful because the old bounds come on the left side of the equality. So basically, the old bounds, when x is 0, the question is, what is theta? That's the lower bound. Lower bound here. And if x is 3, again, the question is, what is theta in that case? So 0 is equal to 6 times sine of theta, which means sine of theta is 0. And again, the inverse of 0, if you look at the unit circle or if you do it to the calculator, that gives you theta equals 0. So you solve for theta to compute the new bounds. I know some people are refraining from computing the new bounds because they don't like it for some reasons and they think, okay, I'm going to go back to x at the end. But I would say that again, it's correct. That's the correct way to change the bounds. And in cases like this, it's probably a little bit faster to do the computation in the end. So if 3 equals 6 sine of theta, then sine of theta is equal to 3 over 6, which is 1 over 2. So then theta is inverse sine of 1 over 2, which is 30 degrees. In other words, pi over 6. So that's in contrast with how you change the bounds when you do the U substitution, because in that case you plug in the old bounds into the function. Here you solve for the new bounds. Nothing fancy really. All you have to do when you change the bounds is to look at your substitution. Doesn't matter which type of substitution you have. And just make sure you plug in the old bounds in the appropriate position, right? It wouldn't make sense to plug in the old bounds for theta because that's your new variable. The old variable is x. Hence you plug in the old bounds on the left side and solve for theta. Okay, and then my integral now becomes an integral from 0 to pi over 6. The top now is 6 sine of theta. The bottom becomes, remember, just like before, 6 cosine of theta. And the dx is 6 cosine of theta d theta, right? So in case we forgot, dx needs to be computed. That's 6 cosine of theta d theta. 6 cosine of theta cancels. And see, now you end up with a trigonometric integral, but one that is immediate. We don't need anything fancy to solve it. So the integral of sine is minus cosine, so that's minus 6 cosine of theta. Plug in cosine of, plug in pi over 6, and then cosine of 0. Let's see, cosine of 30 degrees is root 3 over 2. Cosine of 0 is 1. So that's gonna be 6. Actually, we can cancel this by 2. So it's gonna be 6 minus 3 square root of 3. Okay, so I asked you to think about if you notice something about this problem, and pause for a moment, think about it, and let's see if you actually guessed what I was talking about. And I'll mention what I was talking about in the next page. Okay, so what was special about example 3, right? This is example 3 before. Well, I kind of actually mentioned in passing in a previous page. think about other methods if they are faster. I mean, in this case, I'm not sure how faster it is, but the point is you don't actually need to use trigonometric substitutions. I always think in this order. Is the integral immediate? If not, can it be done with a U substitution? That tends to be faster if it's possible. Can it be done by parts? Then you can think about other things like trigonometric substitutions, because again, those problems can be long. Here, because I have x dx on the top, and because there's a relationship between the derivative of 36 minus x squared with x, right? If I take the derivative of 36 minus x squared, I get minus 2x. I wanted to say minus 2x dx here, but the derivative itself is minus 2x. That suggests that a U substitution will work. Just take U to be 36 minus x squared. Du would be minus 2x dx. We're going to have to move the minus 2 over to the left when I do the substitution. And be careful when we change the bounds. Here all bounds come on the right side, okay? So if x is 0, the lower bound for U becomes 36. And if x is equal to 3, the upper bound for U will be 36 minus 9, which is 27. Remember, the upper bound can be lower than the lower bound. It's not a problem. Just make sure you put them in the correct order. So without any further ado, you can just go ahead and solve this via the U substitution. So that'll be the integral from 36 to 27. That's going to be 1 over square root of U. X dx is minus 1/2 du. 1 over root U can be written as a power. That's U to the minus 1/2. Pull the minus 1 over 2 and then just do the power rule. U to the minus 1/2 plus 1 over minus 1/2 plus 1. So minus 1/2 plus 1 is 1/2. The reciprocal of it is 2. So you end up with minus square root of U between 36 and 27. Minus root 27, if you want to simplify it to make it look like the previous answer, think of 27 as 9 times 3. Root 36 is 6. When you take square root of 9, that's going to be 3. And so this becomes 6 minus 3 root of 3. So don't rush with trigonometric substitutions if you could do the problem using a faster method. Let's move on with another example. We still have to do an example involving a third type of radical. We didn't do an example involving that one. So if you have a radical involving x squared minus a squared, in this case, the substitution is a secant theta. And then the radical becomes, under this substitution, becomes a tangent theta. All right, so let's do carefully an example involving this. So let's do actually a definite, well, yeah, let's do an antiderivative so we can see all the steps. So let's say I need to compute the integral of 1 over x squared minus 1 to the power 3 over 2 dx. Now you may say, well, wait a minute, this doesn't look like square root of x squared minus a squared, but really it does involve, because, you know, if you have a quantity, this quantity x squared minus 1 to the 3 over 2, it's the same as square root of x squared minus 1 to the power 3. And if you pull the x squared minus 1 squared outside, you're still left with square root of x squared minus 1. So actually this method can be extended essentially to any fractional power, if you want, of quantities like this, x squared minus a squared, and so on and so forth. But of course they are useful and meaningful when you have these radicals, you know, when you actually simplify it. You don't have to actually do this to change 3 over 2 in this form, right? But I just want to point out that it does contain a quantity like that. So let's proceed with the substitution right away. Well, I should say one thing to keep in mind here is when you proceed with these problems, actually you kind of have to write it this way, because because you have to simplify that radical with the tangent of theta that I mentioned here. And let's see. X squared minus 1 positive, okay, because it's going to be, let's see, yeah. Okay, so this becomes 1 over x squared minus 1 square root of x squared minus 1. It's positive because it's by definition. All right. I'm a little bit distracted by something else on the page. So anyway, the substitution is going to be a secant theta. That means x is equal to 1 times secant theta, right? Because a is 1 in this case. So secant theta is x over 1. Okay, so pay attention when you write your triangle. Secant is 1 over cosine, right? So if secant is x over 1, cosine is 1 over x. Because when you label that triangle, you have to be very careful to label it correctly. So secant is the hypotenuse over adjacent, right? Or put it differently, cosine is the adjacent side, which is 1, over the hypotenuse, which is x. And then the other side is going to be square root of x squared minus 1 from Pythagorean theorem. So we're going to keep this in mind until the end of the problem. And let's remember the identity that is relevant here. Secant squared theta minus 1 will be tangent squared theta. All right, so then, and also we need dx. Let's not forget dx. Dx is going to be the derivative of secant, which is secant theta tangent theta d theta. And now we finally are ready to replace the integral. So it's going to be 1 over, I could use actually the first integral here, secant squared theta minus 1 to the power 3 over 2, and then dx is secant theta tangent theta d theta. Secant squared is minus 1 is tangent squared, as I mentioned here. So it's 1 over tangent square theta to the power 3 over 2. So pay attention to the algebra here. Tangent squared with 3 over 2, the 2 cancels, and you're left with tangent third here. So secant theta, tangent theta on the top, tangent third on the bottom. And then we can cancel a factor of tangent, and you're left with secant theta, tangent square theta d theta. All right, so what do we do after this? This seems like a dead end because it doesn't look like an integral that we solved before. It doesn't contain an odd power of tangent. It doesn't contain an even power of secant. It doesn't fit the mold to what we've done before. Well, you got to remember that in the end, we don't have actually a rule for all types of problems, right? So in many cases, you have to do some trial and error. One of the things you could do is to change the functions to different ones. How does this look like if I write it in terms of cosine and sine? So granted that some examples like this are a little bit harder because you have to do this trial and error, but you shouldn't give up, because often if you make a little change, like for instance, in this case, changing to sine and cosine, you may see a way about it, on how to solve it. So if I change into sine and cosine, well, remember tangent is sine over cosine. So 1 over tangent, let's put it this way, 1 over tangent squared and secant. So tangent is sine over cosine, 1 over it is cosine over sine. So this piece here becomes cosine squared over sine squared. You can take it separately, right? So tangent is sine over cosine. So if you flip it, it's going to be cosine over sine, but to the power 2. Secant, remember, by definition, is 1 over cosine theta. So you see sometimes you have these hidden simplifications, right? If you do this, you can cancel another factor of cosine. And now I hope it looks better in terms of how you're supposed to go about it. You have 1 over sine squared cosine of theta. Remember, the derivative of sine is cosine. This looks very nicely set for a U substitution. If you take U to be sine, d is cosine of theta d theta. In terms of U, this is nothing but 1 over U squared. Which, if you write it as a power, that's minus U to the negative 1. So it's minus 1 over U. And now you go back to the original variable in 2 stages, right? So U was sine of theta, so that's minus 1 over sine. From the triangle, sine of theta is root x squared minus 1 over x. And 1 over that is x over square root of x squared minus 1 plus a constant c. All right, so in exam and tests, I will avoid examples like this in the sense that I will avoid problems in which you will have to spend too much time guessing through the method. I mean, I will stick to the ones that are basically suitable to, I mean, like amenable to one of the techniques we learned. However, in general, be prepared to, how shall I put it? Be prepared to improvise on the spot, essentially. So if there's no obvious way on how to solve it, maybe you could change it to a different way. So you do a little algebra and see if it looks better. So I think that's it for today. Let me think a little bit. Yeah, I think that's it for today, and we'll, yeah, actually, no, sorry. Let's do one more example, and that'll be it. So we'll stick to one more page. Okay, so one more example. You will see at the end the reason why I wanted another one. There's a part at the end where people sometimes get confused on how to write the answer, and I want to go about this type of problem as well. So this is we can go a little bit faster. I hope you get the hang of it. Look at the radical. It calls for the substitution 3 secant theta, right? So it's gonna be x equal 3 secant theta. Isolate secant. Draw that triangle. So secant means hypotenuse over adjacent. So you can take hypotenuse to be x, adjacent to be 3. And once again, from Pythagorean theorem, the opposite side is root x squared minus 9. So let's keep this in mind for the end of the problem. Then the derivative of 3 secant is 3 secant theta tangent theta. And now we can proceed to integrate. Replace x with 3 secant. So it's going to be 9 secant squared minus 9. 3 secant theta to the power 3. And then dx becomes 3 secant theta tangent theta d theta. All right, so the top becomes 3 tangent. let's see, on the bottom we can expand that a little bit. 3/3, secant third, secant third, and then 3 secant tangent. We can cancel 3 secant, and so you're left with 2 over here and 2 over here. Oh, we can cancel another 3 on the top, so you're left with really 3 on the bottom. So it's going to be just 1/3, the constant, and then tangent squared over secant squared. Again, before you think about how you handle this, see if it's easier maybe if you write it in a different form. So first of all, notice it's not of those types you could solve. It's not like something times secant squared. So don't think about, oh, I have secant squared, it's going to work with substituting u equals tangent. Doesn't work that way because it's not times secant squared, it's over secant squared. But again, as a rule of thumb, let's see what happens if I replace these in terms of sine and cosine. So tangent squared on one hand is sine squared over cosine squared. And remember, secant is 1 over cosine, but 1 over secant is just cosine, right? Again, if it's not clear what I'm talking about, look at in the corner here. So secant theta is 1 over cosine. So of course 1 over secant theta is just cosine of theta. So it's really 1 over secant squared is just cosine squared theta. So wouldn't you know it, cosine squared actually cancels. So all you have to integrate eventually is sine squared theta. Okay, now it's time to remember how you handle sine and cosine with even powers. And when you have even powers, you have to use the double angle formula to reduce the power. Again, go back to the previous section if needed. So we know that sine squared is 1/2 quantity 1 minus cosine of 2 theta. And now, let's see, we can pull out 1 over 6 and integrate. So the integral of 1 is theta, because theta is your variable, right? So that's d theta. And the integral of cosine of 2 theta, it's a U substitution for 2 theta, which you could do in your mind, hopefully. So that's minus 1/2 sine of 2 theta. Okay, so this is where it gets tricky at the end, which is the reason why I wanted to go about this example. Now, if it was a definite integral, then things are easier because you change the bounds, you plug in whatever you have for theta, but this is an antiderivative, so how do you go back to theta? Remember, your triangle gives you trigonometric functions of theta, so you have sine of 2 theta. Here is another double angle formula that is very useful to keep in mind. Again, you can write it down, you don't have to memorize it. Sine of 2 theta is 2 sine of theta cosine of theta. In fact, these double angle formulas, personally, I like them to memorize them like this. Cosine of 2 theta is well, let's leave it at that. I wanted to put all the others, but let's not overcomplicate here. So sine of 2 theta is 2 sine cosine. So that's how you can relate it with a triangle. And then theta is just the inverse of secant, right? I mean, if the substitution was secant theta equals x over 3, you can simply refer back to theta itself by taking the inverse trigonometric function that you use in the substitution. I know it looks overly complicated, but that's the way it goes. Because your substitution was x was replaced by a trig function. So theta itself will be the inverse of that trigonometric function. So to complete here the answer, if I distribute 1 over 6, so it's 1 over 6 theta minus 1 over 12. Sine 2 theta is 2 sine cosine. And now you can replace finally everything in terms of x. Theta is inverse secant of x over 3. Sine of theta from the triangle is opposite side over hypotenuse. cosine from the triangle is adjacent side over hypotenuse. So these are from the triangle. And then plus a constant c. Maybe you can simplify it, 3 and then it's 1 over 2, but that's it. Okay, so that situation happens when you end up with a double angle formula at the end, because that's when you have theta by itself when you integrate. So I think we have enough before you guys start going over the homework, and I'll see you next time.